Okay, so when we see that there's a force, what we do is we draw diagrams. In science, we always draw diagrams to show what's going on with something. Okay, so these things are called force arrow diagrams. Right, and what you're going to basically do is you're going to show that an arrow represents a force, and what you're going to do is you want to show, because remember, force has two things. It's got a direction and it's got magnitude. And so how you show direction is what direction that you're doing it. So this one right here, right? These arrows are pointing right. So that means that the force, so something is pushing the object right. Now how do you show magnitude? How you show magnitude is how long you make your arrow, right? So if you look at it, the longer the arrow shows the stronger the force. Okay, so that's how you show magnitude on an arrow. Now, sometimes too, you'll see numbers that go with it. Within our class, it's really hard sometimes to find like how strong a force is because we don't have something that measures that. But anyway, the stronger the force, the longer the arrow that you're going to draw. So if I'm going to draw an arrow and I know one's stronger than the other, you got to make sure that that arrow is longer. Okay. All right, so let's show some examples. All right, so one is called when, let's say one situation is called a balance force. Okay, and balance forces is when both arrows are equal in length on both sides. So in other words, there's no change in motion. Okay, in other words, the object is going to stay where it's at. So if I have something, if I look at it, this square, if I have something that's pushing 30 newtons left and 30 newtons right, it's not going to go anywhere, right? It's just like tug of war where two people of equal strength are pulling on it. What happens? Nothing happens because those forces are really, really, really equal. All right, it's basically like nothing is pushing it, and that's what balance forces mean, right? On the flip side, where it's unbalanced forces, okay, just like what it says, unbalanced, it means that one force is stronger than the other side. And that usually causes some kind of change in motion, whether the object is going to speed up, slow down, all right, or it's going to start moving if it wasn't moving to begin with. So, for example, in this one, we got one that's moving right, 150 newtons strong. Another one that's being pushed 40 newtons to the left, all right? So obviously, if you just look at it, you can totally tell just by also the arrow lengths, right, that the object is going to go moving to the right because the arrow that's showing that it's being pushed to the right is that much stronger. Okay, so the object is now going to change its motion. So that's what we call unbalanced forces. Okay, so now when we have numbers, we calculate how strong one force is to another one. So let's take this picture, and I want you to obviously draw this picture, right? Same with the other two sides. Sorry, I forgot to mention those, but you should draw those drawings. If you didn't, go back and draw those, all right? But what net force is, so this is another equation. So the equation for net force, so in other words, basically what you're trying to find is the sum of all forces, right? So what you do is you add up all the force on one side, and you subtract it by all the forces on the other side. All right, so for example, let's say that there's three things pushing this object right here. All right, so we've got one force that's pushing 35 newtons one way, to the right, I should say. So this one's going to the right. And I've got two forces pushing to the left. All right, so what I do is I add up all the forces on one side. So I've got 35 newtons pushing to the right. And I subtract, right? So I'm going to go like this. And I'm going to subtract the two forces on that are pushing to the left. So I go 15 plus 15. Okay? So if I look at it, it's 35 minus 30. So it's 5 newtons. And I have to then, I can't stop there. And that's where most kids make the mistake. You have to, again, remember forces. It's got two things. Magnitude, which I got here, and direction. So the direction is it's 5 newtons right because it's 5 newtons stronger going right because 35 is bigger than these two combined. So my answer to this is it's going to move like there's one force going 5 newtons to the right. So this object would move at a pace of, 5 newtons right if I were to do this in real life. All right, so let's do another one. Let's do another calculation. So now this time, right, we've got 4 forces. So this gets a little bit tricky now because before all we had was left and right. So now what happens when we have up and down with it? So there's 4 things that we want to look at first. Number 1 is it balanced or unbalanced? I'm hoping that you can look at it and go, wow, none of the forces are really equal to each other. So right away you should notice that this is a balance. I'm sorry. Wow, I almost made a huge mistake. This is an unbalanced forces, right? And when I see unbalanced, I should know that, hey, this is definitely going to have a change in motion, right? Because balanced means no change, unbalanced means for sure change. I can already tell you, right, just by looking at these 2 numbers right here, that it's going to definitely for sure go to the right. Okay? So next thing is let's calculate my net force. Now this is where it gets tricky when you have 2. So I'm going to put net force equals NF. And the first thing you have to do is this. This is actually a 2-part problem. I can only look at left and right together and up and down to get separately. So what I do first is I go 65 newtons minus 20 newtons. Okay, now I'm subtracting again because these 2 arrows are going in the opposite direction. So I'm not going to add those. So now I got 45 newtons. Remember, I got to say what direction. So I know that my right one is stronger. So I go right. Okay, now I've got to do my ups, or my down and my up. And I have to actually separate that. I can't add it to that. Okay, so I actually go 20 newtons minus 10 newtons. Okay, again, I'm subtracting because these 2 arrows are in opposite directions. So then I go 10 newtons. And again, my downward arrow is stronger, so there you go. So my actual net force is these 2 combined. It's 45 newtons to the right and 10 newtons down. So I actually have 2 answers to that. I have to have an up and down component and a left and a right component. So then when it says which way will the object move, it's going to move. So it's going to move right and down. How do I know that? Because I said it right here. In the force, when I calculate my net force, that tells me which direction it's going to go. Because it's going to move downwards and it's going to move right. And that's my answer to that question right there. So that's how you do force arrow diagrams for things that go up, down, left, and right. Alright, so a few more things. So, and this is going to be important for your car project because obviously every single person's cars are not going to weigh the same. The question is, okay, what happens when you change the weight of something? So I'm going to run this cool looking simulation. And I'm actually going to, for extra credit, have you guys maybe do this a little bit. So the first thing is this, and it's pretty obvious, but I want to just show you visually what happens. So I've got one weight, right? So this one's just one guy. He's 80 kilograms. He's on a skateboard. And then this guy right here, then I'm going to show you what happens when you put a refrigerator on him. That weighs 200 kilograms. So I've got a guy who only weighs 80 kilograms here. And then I'm going to have same thing with same skateboard, now have 280 kilograms. And what happens to, I'm going to look at 2 things. Which weight would be easier to push, and what do I need to do to push both at the same speed? So I'm going to go to my guy right here, and actually I'm going to go here, and I'm going to put my guy on here. All right, so he's now 80 kilograms. So I'm going to show my values and stuff, and here's my little speedometer. Now if you notice, I'm going to push him to the right, and I want you to see how much force it takes to start moving this guy. So I'm going to move him. So if you look, right, I already have just 46 newtons, and he's moving. Okay, so he's moving pretty good, solid. And you can see that I'm picking up speed and stuff like that. So I'm going to pause it now. All right, now let's see what happens when I reset all this. All right, again, remember, I was at 46 newtons. Now I'm going to put a refrigerator on him. And now I'm going to go back to the 46 newtons. And I'm going to push him at 46 newton strength. Oops. Stop. Okay, let's stop this again. Okay, let's go like this. Oh, I forgot to put the guy on him. Hold on one second. Hold on. Let's start again. Okay, so let's put the guy on with this. Remember, before, without the refrigerator, when I tried to push him 46 newtons, he moved. So let's see what happens when I try to do 46 newtons this time. Okay, look at how much slower I'm actually pushing him. A lot slower. Okay, so if I look at it, which one would be a lot easier to push? Okay, I hope that you can say that, hey, let's move this guy away. That obviously this situation, right? Less weight equals easier push. And I think that should be pretty obvious, right? If you just pulled your chair, right, and then I put 100 pounds on there, all right, which one would be easier to pull the chair? Obviously, in order for me to do that, I would need to, right, push it, or it would be harder to pull the 100-pound one. Now, what would I need to do then to push both at the same speed? Okay, so let's look at it. Right? If I have, let's take this off again, right? And if I wanted to push him again, like what would I need to do? Oops, let's reset it. So what would I need to do to push this guy? So let's say that I pushed him at full speed. Or actually, I'm sorry. If I was pushing him at this speed, like 136, and I let go, and I'm going, see up here, the speed right here. What would I need to do to make him go that fast and that speed really quick? Okay, I would hope that you would say, okay, if I have this and I'm pushing him, I'd probably have to push stronger to get the guy to go the same speed, right? So if I did 136 again, I'm just barely pushing him. But if I really wanted to do it, look at my arrow that I have to get a lot stronger to get him to go moving that quickly at that speed. Okay, so if I go back to my notes, what do I need to push both at the same speed? All right, I'd have to, for this one, I have to push harder. So in other words, I need more force. And again, I hope that's pretty obvious for a lot of you guys that, hey, if I had a chair that had nothing on it, and then someone sat in it, and I pulled, I would probably have to pull the chair with the person on it a lot harder in order to go the same speed as I would pushing it, right, with nobody on it. So pretty obvious.